Okay, kiddos, here's part two of looking at simple harmonic. So, where are we? Oh, yeah. So, we watched a little video, and here in our study of simple harmonic motion, we consider the mass on a spring system first. So, this is set up two ways, and this is more difficult to do in practice. This is pretty easy, okay, because if we hang a spring from the ceiling and hang the mass from it, there's very little friction involved in the system. The other sort of ideal system is where we have a tabletop and the spring is attached here, so the spring can pull or push, and the mass is frictionless on the table. So we know that this doesn't really exist. I suppose we could do something with a little rolly cart, and that might be fun, and then a nice taut spring. But so this is the one that we'll actually do in class, but when you see it in a textbook or something like that, it's either this system or this system, but they behave exactly the same. So what we said in the previous video was that simple harmonic motion results when the restoring force is proportional to displacement from equilibrium. Yeah, I'm going to say that once more. When the restoring force is proportional to displacement from equilibrium. So this is called Hooke's law. Hooke's law, and it describes this system, mass on a spring. And so this is the restoring force. Let's zoom in here. We call this the restoring force, and that's the force that brings the mass back to equilibrium, the force that brings it back to its resting position. This x, so we're used to using that for displacement, so this is displacement from equilibrium okay, or position, distance, so the distance away from its resting place. That sounds kind of morbid. And then K, this is the spring constant. And the spring constant is a measure of the springiness. Springiness. That's totally a word. You should ask your English teacher. The negative in the equation comes about because if we have a situation like, here's our spring, here's our mass, excuse me, if our displacement is in this direction, you can think about it, in which way would the force be? And well, that's this way. So the force and the displacement are going to be in opposite directions. If we were to pull the mass this way, the spring is going to pull it back this way. So again, because these forces, because the displacement and the force are in opposite directions, that's where the negative sign comes from. So the springiness, you can think about, well, what would units for spring constant be? And you don't just wonder, you think, well, I know that force has units of newtons, and I know that displacement or distance has units of meters. So if we were looking at our spring constant, K has units of newtons per meter. So it's a measure of how much force the spring exerts when we stretch it by a certain amount. Okay, and a typical spring constant, I think for the little springs that we're going to use in class, it's something like 50 newtons per meter. Remember, a newton isn't a very large amount of force. What's the conversion between newtons and pounds? Your brain's thinking, and correctamundo, about 5 newtons is 1 pound. LBS. I guess it would be an LB, not an LBS, sorry. So that's Hooke's law. So this is our formula that we use for determining the force basically exerted by a certain spring based on how much it is stretched. And oh my gosh, look at all these terms. Yeah, this is why we created a separate video for here. So, amplitude, period, frequency, equilibrium position, periodic motion, etc. So, we're going to take a look at this situation, and we're going to talk about these things. So, what happens if I take this mass, here is the equilibrium position, right? It's at rest. And if we displace it by a certain amount, so now the mass is over here, so we have some displacement. We know that there would be a force in this direction, restoring it to its equilibrium position, and that would be the pull, that would be the pull of the spring that we could calculate using this formula. And if we let it go, so imagine that this thing is, there's no friction going on here, and if we let it go, it's going to go boing, 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 back and forth. And if we were to actually look at, which is exactly what we will do, if we were to look at position as a function of time, so let's look at position as time goes on. So in this thing, we pulled this to the right, we gave it some positive displacement, right? If this is equilibrium, we could say that's positive displacement, this is negative displacement. And so when time starts, it's up here. All right, we pull it out here, and then we're gonna start the stopwatch just as we let it go, and it goes boing, 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 and it would look, it would look something like this. So we'll get into the sine, cosine graphs and equations for them and all that good stuff. But for now, let's just take a look at the motion, okay? So right as we release it, it has some maximum displacement, right? And then time goes by and it goes back to equilibrium, so that is when the mass is here, and then it's going to slide over here, and our mass would be over here, and that corresponds to this, the displacement that is a negative amount. And then it would slide back to equilibrium, so from here it's going to slide back to here, and so on and so forth. So, when we talk about this vocabulary here, this is what it relates to. Our, let's see, oh yeah, you can see this. All right, so this is our amplitude. And amplitude is, we could just call that our maximum displacement. And, you know, we want stuff to sound fancy. Maximum displacement, what does that mean? That is the as far away as it gets from its resting place, from equilibrium, from the middle. On the graph, you're probably wondering, what's the amplitude? Good question. Amplitude, or amplitude. So we don't give a positive or negative to amplitude. It's just so scalar quantity, right? Not a vector quantity. So that would be our amplitude. Maybe I'll write it, but I don't want things to get too confusing or too jumbled up. Amplitude. Okay. So what else? We have our equilibrium position, so that is this line in the middle. Let's label that. Hey. Yeah, I'm going to stick to the colors. So this guy here, equilibrium position. And when we talk about, our next thing was period of oscillation. So amount of time for one complete cycle. So if we talk about where it starts, it's starting over here, right? And then going won't, when won't, that would be won't and then won't. That would be one complete oscillation. So we can say this is period of oscillation. And fortunately for us, we have already studied rotational motion, so this term is pretty familiar, and you know how it relates to the frequency of oscillation. You're nodding your head yes. Frequency and period of oscillation, those are sort of, no, they are exactly reciprocals. So let's write this out. Period of oscillation is the So time for, I'm going to say out and back. Try to simplify it a bit. Time for out and back, or one complete oscillation. Fine, I'll write it. One complete oscillation. And frequency is, excuse me, here's our formula. F equals 1, that's a 1 over T, or we could write T equals 1 over F. Frequency is the oscillations, you guessed it, per second. So seconds per oscillation, that's period. Oscillations per second, that's frequency. There we go. So if you're looking for, we can't really graphically represent frequency, but we can definitely graphically represent the period of oscillation, and then we just do 1 over that and we get the frequency. Okay, so what else do we have? We talked about the amplitude, we talked about the period of oscillation, where'd that go? Period, oh, frequency, equilibrium position. Periodic motion is just something that repeats itself, which is these systems that we'll be studying. So when this thing is moving, let's talk about how it's moving. So we're considering the system, this thing's moving back and forth and back and forth and back and forth and back and forth. So it looks like this. When it's out here, all right, for an instant it is stopped. It's like throwing a ball up into the air. We say that up at the top, well, straight up into the air, all right, so you throw a ball straight up in the air. At the top of its flight, its velocity is 0 for a moment. So what we can say is out here, let's zoom in on this. What we can say is out here, we can say velocity equals 0. All right, so that's at its maximum displacement, velocity 0. We can also say that the acceleration is at a maximum. So when the mass is as far away as it can get from equilibrium, that's when the force is the greatest. And if the force is the greatest, F equals ma, we know that the acceleration would be the greatest. Okay, so 0 and then speeds up, and then is momentarily, there's no force on it, and then it's going to slow down and then speed up and then slow down and then speed up and slow down, etc. So in our middle region, we can say that the acceleration is 0, and it's 0 because there's actually no force acting on it. It is the momentum of the mass that keeps it going through equilibrium. We can say that at this point it's going its fastest, so velocity equals a maximum. And then what about kinetic and potential energies? Nice energy color. So out at the end here, we say that, you know, if we let it go, it's going to start moving. So we can say that potential energy is a maximum. And when it's going fastest here, this is where kinetic energy will be a maximum. All right. And then I think that I just want to tell you one more thing, because this is so fun. We got, I think on your formula page, it's going to say this, U sub S. So this is potential energy for a spring, and it's equal to 1/2 kx squared. Kind of cool how that looks a lot like kinetic energy is 1/2 mv squared. So let's call that potential energy, PE. Alright, so potential energy, our formula is 1/2 kx squared for this system, right, when it's displaced. So the greater the displacement from equilibrium, the greater the potential energy. Out here it would be a max, and when it's going fastest, kinetic energy would be a maximum. Okay, we're done with part 2.